Hi, welcome to the live session for the NPTEL course on numerical analysis. I'm the instructor S. Baskar from Mathematics Department of IIT Bombay. Uh, I hope you are enjoying the course and you are following all the lectures nicely. Uh, so in this live session, uh, we can take any questions that you may have, and we'll try to answer that. And also, I'll try to explain you some concepts which I feel is difficult, or I will give some overview of what happened so far, so that you can keep this as a revision session. In between, if you have any questions, you need not wait for me because I will be talking. Anytime you can interrupt me and ask questions on whatever doubts you have, not necessarily what I am talking on. Uh, so maybe I will just wait for a few minutes for you to ask some questions. Then I will start briefing on the topics that we have covered so far. I hope we are into seventh week, and we are now learning some numerical methods for nonlinear equations. Okay, so there is one query. Uh, yeah, so Uh, Chetan is asking, sir, will there be negative marking, and please specify duration of exam too? This is a question regarding exam. So maybe Bharti madam can tell if there is any uh, negative marking. Yeah, so we are in the seventh week, and is there any negative marking for the final exam or assignments also? And the duration of the exam, Madam can clarify on this. There is no negative marking. Okay, so that's nice. I hope there is no negative marking for both assignments as well as exams. And okay, so the duration of the final exam is 3 hours. Okay, so that's nice. I hope Chetan got these answers from Madam. Uh, okay, so you can ask some questions if you have doubts. Generally, also on the applicability of methods and so on. Okay. Uh, So basically, our course is uh, covering the numerical methods and their error analysis for problems that are quite often occurs in scientific areas and scientific and engineering areas. The first point of interest in numerical analysis is how computers make errors. Okay, It's not that only humans make error, even computers make deliberate errors. Okay, so human makes careless mistakes, okay, as errors. But computers don't make careless mistakes when they are calculating. Okay, so that much is guaranteed, but they have some deliberate errors coming because of their limitations in their memory. Okay, computers have only finite precision memory. Because of that, they cannot store certain numbers in their full accuracy. For instance, 1 by 3 is a number, right? So that number can be represented as 0.333 and it goes on, okay? So it endlessly. How many threes are there in the decimal place? Well, there are infinitely many. Keeps on going. Okay, so when you try to store that on a computer, obviously computer has only finitely many memory located for the so-called mantissa. That is the part that is after the point is the mantissa, if you recall. And therefore, it cannot store numbers exactly, right? It has to truncate that number. So in our first chapter, we first introduced how the computer stores these numbers, and we considered two simple ways of approximating these numbers. One is chopping, and another one is the rounding approximation, right? Then we saw how these approximations are handled. First thing, we introduced kind of measuring tool for how much error we get in this approximation. Okay. So by counting the number of significant digits, we have given a mathematical definition for that. Number of significant digits. And then we saw how this error, which is created at the storage level, gets propagated when we use them in our calculation, like any arithmetic calculations like addition, subtraction, multiplication, and division. And we also concluded from here that all other operations are relatively better, but subtracting two positive number is going to be the most dangerous operation, in the sense that even a small error can be magnified significantly as we go on in our calculation that involves subtraction of two positive numbers. Okay. Then we introduced another important concept called the condition number of a function, because once we understood the errors and error propagation in simple arithmetic operations, then we were interested in seeing how these errors can propagate when we go to evaluate some functions on a computer. So in that way, we introduce the condition number of a function and try to see that if the condition number is very large, maybe the function is considered to be unstable in computation. Okay, so if the condition number is small, it doesn't mean that it's stable. Then we also studied when we can conclude that a function evaluation is stable or unstable. Okay, so these are the things we saw in the first chapter, which would have run in the first week, or maybe first plus something in the second week also. Okay, so if you have any questions on this chapter, you can ask me. I will just give few minutes pause in my discussion so that you can ask questions. It doesn't mean when I'm talking, you should not ask. You can also stop me and ask questions when I'm talking also. Okay. So just I will give you 2 minutes pause so that you can ask. If you don't like to stop me in between, you can ask now. Okay. So then I think we started with numerical linear algebra. As I have told in the video lectures that we will be taking up some simple problems and we will be studying various numerical methods applied to those problems so that we get uh, experience and knowledge in handling numerical methods for various problems, and also if needed we can develop our more own methods if we are familiar with them. So in that way, as a first uh, chapter, we have taken linear algebra problems. In that, the most common problem that we come across is solving a linear system, right? So solving linear system has many applications. I need not list them. You must have seen them in many applications of science and engineering. Um, so there are basically two types of methods that can be used in solving linear systems. One is direct method. Okay? So the direct methods are those which gives us exact solution. Okay? Means there is no error involved in that solution if we compute them manually. Okay. Uh, of course, if you implement them on a computer through computer program like Python and so on, of course, the limitation of the finite memory precision of computer will play in role, and therefore you may get an approximate solution to your system, even though it is a direct method. Okay. So therefore, in that way, you can say that direct methods always give exact solution if you compute them with infinite precision. Okay. Uh, Infinite precision, in a sense, can be thought of as representing all the numbers in their fractional form. For instance, 1 by 3 is represented as 1 by 3 only, not in its decimal form 0.333 and so on, right? So if you represent them in fractional form, then they are like written as some p by q form, and p and q are integers. Therefore, there is no question of finite precision approximation. Okay. So therefore, in that sense, direct methods are going to give us exact solution. So that is kind of quite encouraging. because we get more accurate result. Even if you put on computers, direct methods are definitely going to give us uh, maybe better solution, mostly because they don't involve any error at the mathematical level, right? However, these methods are not often preferred because their computational cost is too much. Okay. So these are the important things that we have to understand. And not that they always give good result also, because sometimes this arithmetic error, which is actually the error coming due to the approximation of the numbers by the computer. Okay. So these arithmetic errors can be dangerous than even the error that is coming from your mathematical approximation, which we call as mathematical error. Okay, so therefore, the direct methods are not always preferred, and in particular, they are not mostly preferred because of their computational cost. Okay, it means how much time it takes to compute solution. Okay, on a computer. So these are the things which we have to understand in this chapter, and they are crucial for us in selecting good methods. Okay. So therefore, what we did is we first took the direct methods and we introduced the most important direct method in linear systems, that is Gaussian elimination method. Okay. So the Gaussian elimination method, in a sense, is the most costliest method in terms of time taken by the computer to arrive at a solution. Okay. We, of course, deal only with invertible matrices as the coefficient matrices. Therefore, we have unique solution for sure. And so we, therefore, you can also invert the matrix and get, that is much more difficult. Whereas Gaussian elimination method first converts the given coefficient matrix to an upper triangular matrix, right? So that is called the elimination process. And once the elimination process is done, then the next step is to go for the back substitution. Okay, so back substitution is done, and that's it. We got the solution. So these are the two steps that are involved in the Gaussian elimination method, and we have shown through some examples that in certain cases, the Gaussian elimination method as a name method means you don't have any extra adjustments in the system. Just go with the elementary operations and get a upper triangular matrix. Okay. So there is a question from Chetan again. Sir, I am also studying linear algebra in my college, and there is a topic, simultaneous triangulation. Okay. That I cannot find content on internet. Can you please tell me what it is, like what we do in it? Okay, so simultaneous triangulation. I have not heard of this word, maybe. Uh, Simultaneous triangulation. See, generally, Gaussian elimination method uh, is uh, is reducing your given system to an upper triangular system. Similarly, you can also do lower triangular system, which we have done with LU decomposition. I'm not sure whether you are talking about the LU decomposition in simultaneous triangulation. I'm not sure about that. Is that something like LU decomposition that we do in this course? Maybe you can reply for that, then we can go ahead, because LU decomposition also does simultaneously decomposes the matrix into a lower triangular and upper triangular matrix. So therefore, the simultaneous triangulation might mean that. Okay. If so, I'm just coming to that in a few minutes. Okay. Continuing with our discussion, this Gaussian elimination method sometimes amplifies the error. Okay. Especially when there is a rounding error involved in it, then even though it tries to get the exact solution, but because of the rounding error and its propagation into the further steps of the Gaussian elimination method, finally you may land up with a so-called solution coming out of the method, which is nowhere near to the exact solution. Okay, so that's a serious problem with Gaussian elimination method when you go to do it on a computer. Okay. So therefore, one has to be careful with it. To reduce this kind of errors, we have introduced um, another intermediate step in the Gaussian elimination method called the partial pivoting, where we actually take the at every step, we consider the maximum of all the columns that are need to be eliminated. In that step, we take the absolute value of them, including the one which is going to be the base equation, and then take the maximum of it, and then just replace the first one with the one which got the maximum. Okay, so that's the kind of adjustment that we do, which is called the partial pivoting, and that often increases the accuracy. That's what we illustrate in that chapter. Okay, so partial pivoting is makes this method more efficient in terms of controlling the error, and we call this method as a modified Gaussian elimination method. Okay, so that's what we do with that. And then to show that Gaussian elimination method indeed takes a lot of time. To illustrate that, what we did is we try to calculate all the number of operations involved in the method. Okay, so number of additions and subtraction, similarly multiplication and division, and then try to see how many operations totally involved in it. So then we found that the number of operations involved in it is a order, that is big O of n cube. Okay, so that's quite costly, because by increasing one dimension in the system can make it n plus 1 cube it will become, right? So that's going to be very costly. Okay, so therefore that is one reason for why people don't prefer to go for Gaussian elimination method, and this is also there with the LU decomposition, which Chetan may be calling as simultaneous triangulation. I'm not sure. Maybe you can tell me. So then we also introduced another methodology, which is LU decomposition. And this is just a decomposing, that is factorizing a given matrix into a lower triangular and upper triangle. The purpose can be anything, but we use this factorization in solving a corresponding linear system for a given right-hand side. Particularly, this is useful when we go to do the inverse power method. To recall, in inverse power method, we have to solve a system a y equal to x, where x is the given right-hand side vector. And in power method, the concept is an iterative method. Therefore, it keeps going on from one iteration to other iteration, where the right-hand side only changes, but the left-hand side remains the same. A y equal to x, and x changes, you have to find y, whereas A is the coefficient matrix is always kept fixed. Okay. So therefore, in such situations, what you can do is instead of every time going for some linear system solvers like Gaussian elimination, or later we had other iterative methods, you can factorize A once and give, okay, into LU factorization, and then keep applying this LU factorization to get the solution for a given right-hand side vector. So that is a very comfortable way. In a sense, you are using a direct method. Therefore, at least at infinite precision, it gives the exact solution. And at the same time, you are not every time factorizing it. Therefore, it's a good idea to go for LU factorization. Okay. So we learned do little and proved factorization. So you have to keep the definition of do little. Once you understand do little, proved, it just is a mimic of that with a minor difference. That's all. Okay, therefore, you just have to keep the definition in mind, and then you can just work it out in the exam also. You don't need to really memorize their formulas, how they look. In fact, in many of the methods that we discuss in this course, you don't need to remember the formula, okay, the final formula. You just have to keep the idea in mind, how these methods are derived. Okay, so once you have that idea, even in the exam, you can just take few seconds to just derive the formula and then use them. Okay, therefore, when you are learning the subject, try to understand the instead of memorizing the formula, try to understand the derivation of the formula. There's always some catchy uh, ideas that you will not forget, but they will easily give you the final form. For instance, such things happens in nonlinear equation. They are all geometrically very rich ideas behind deriving those formulas. Here also in Doolittle, it's very simple. You have a matrix A, which you have to write as LU decomposition, right? Just let me try to write and explain. Let me see whether I can do that. Um, sure where that. I'm just seeing how to share the so that window. Got I got okay. Yes. Okay. Let's see. If you recall, in the Doolittle factorization, you are in fact in all the LU factorizations, you have to write your given matrix. So this is the given matrix uh, into lower triangular matrix. This is lower triangular and into the upper triangle. Okay, so this is the upper triangle. So let's take the 3x3 system, A11, A12, A13, and A21, A22, A23, A31, A32, A33. Okay, so then in Doolittle, you just have to put 1 on the diagonal and zeros here, and you give L21, L31, L32, and upper triangular can be anything. So U11, U22, U23. Here it is 0, but here you have U12, U13, U23, and so on, right? So this is the Doolittle factorization form. Once you just remember that only these diagonal elements have to be 1, you don't need to remember what is L21 equal to, what is L22 equal to. You see, you can just multiply this matrix with this matrix and then compare it with the corresponding this one. For instance, your L21 into U11 should be equal to A21, right? So from there, you will get L21 is equal to A21 divided by what is U11? U11, it's very clear. 1 into U11 should be equal to this one, right? So this 2 should give you this. That implies U11 is equal to A11. That you plug in here, you got L21 as in terms of the known numbers. See, all these A's are known to us, which are on the left-hand side, right? So that in this way, you don't need to remember all these expressions, okay? You just have the idea of how to get them. In the exam itself, quickly you can, if any question comes on that, you can quickly get the formula by doing the simple multiplication, and then you can get the formula, plug in the numbers that are given in the exam and get the answers, right? So therefore, what I'm trying to say is in like this, in many methods, you don't need to really remember the formulas. Okay. Okay. Nazir is asking one question. Good evening, sir. Whether all questions in the exam will be multiple choice question, should we carry calculators? I'm not sure whether you can carry the calculators. Again, Bharti madam can tell us. Mostly the calculators are inbuilt in the exam, in the computers itself, that on which you are taking exam, but Bharti madam can confirm that. Regarding whether all the questions are multiple choice questions, I think it's not like that. You have some questions which are numerical questions, in which case you have to calculate and there will be a fill in the blanks and you have to give some numerical value in that fill in the blanks. Okay, and then there is a range. It's something like how you have in the in the you have in the assignments, right? So you have some questions which are numerical questions. Then there is your answer, if it lies in a range, it's correct, otherwise not correct, kind of thing. Okay. Otherwise, therefore, there are questions which needs calculation. They can be either fill in the blanks, even some questions which are multiple choice can also have some numerical value, right? So there also you may have to calculate. Okay. So in multiple choice also there are MSQs. Okay. Means there may be multiple correct answers, and some are MCQs, means there is only one among the 4 or 5 choices given is correct. Okay, so all these type of questions are there. Therefore, there are 3 types of questions basically. One is the numerical fill in the blanks, and other is multiple choice. Within multiple choice, we have 2 types. One is single correct multiple choice and multiple correct multiple choice. Okay. In the multiple correct questions also, there may be some single correct. Okay. Or there may be all the answers are correct. Okay. So like 4 choices are given, even 4 may be correct. Okay. So these kind of possibilities are there. In that sense, the multiple choice with multiple correct answers, which is generally called as MSQs, they are little difficult. Okay. I'm not sure, again, Bharti madam can answer us whether the MSQs have partial marking. Okay, so madam already confirmed that there is no negative marking, but in some exams, what happens is, suppose two choices are correct, and it's a 1 mark question, and you choose only one, then they may give half mark. Okay, such exams are there, but I don't know in NPTEL what is followed. Okay, so therefore, these are the types of questions that we have. I hope Nasir's question is answered. So please ask questions even if I'm talking. Okay, so I will talk for some time, then I'll stop and come back and answer your question. So there's nothing wrong with that. Don't hesitate to write questions in the chat box. Okay. Okay, so let me continue with the discussion that I was trying to give you idea that you need not memorize all the formulas. In that way, there are many formulas, okay, in this course. In fact, many students in our institute also will complain that we have too many formulas to remember, okay. So strictly speaking, you don't remember them, most of them. Not all, but most of them, you need not remember. Like this, if you take Doolittle factorization, there are many terms. Like every term, every element in L and U have their own expressions. So therefore, you see how many expressions are there involved in this. If you start memorizing them, it's very difficult. This method itself will have so many. U11 equal to A11, and then L21 is equal to A12 divided by A11, right? Similarly, U12 will have its expression, U23 has its own expressions. Okay, so if you start memorizing them, that's going to be very difficult. Okay, but you just remember this structure, how Doolittle factorization will look like. Basically, you need a L which has all its diagonal elements as 1, and then U, which has no such restrictions on the diagonal elements, but it is an upper triangular matrix, that much. Once you know this, you write the product and then get the expression. So you can do it in the exam hall. Similarly, crude factorization is going to be the same idea, but now the diagonal elements of L can be anything, L11, L22, L33, doesn't have any restriction on their values, but the upper triangular matrix has all its diagonal elements as 1. Okay, again, you see the idea is just similar. Okay, you have to write this equation and then multiply on the right hand side the L elements and U elements, and then compare them with the left hand side known matrix. So A is given to us, right? So we know those numbers that are sitting on the left hand side. It is given in the problem. So once you get those expressions, you will get the formulas for each of these elements. Okay, so that way you don't need to remember. Like this, many methods have a very intuitive or very simple way of deriving them. Okay, so you don't need to really memorize such methods, formulas. Okay, so that's the idea. So this covers the direct method, okay, for linear systems. Then we went into iterative methods. In iterative methods, we mainly studied Jacobi method and Gauss-Seidel method. Jacobi method is very simple. Again, the idea goes without any need of memorizing it. So let me just recall the idea. Okay, so let me recall the idea of Jacobi method. It's another illustration for why you should not uh, remember or memorize the. Yes, okay. Okay. So you again have A x is equal to B, right? So let's take this as A11, A12, A13, A21, A22, A23, A31, A32, A33. And then this is x1, x2, x3, and you have b1, b2, b3, right? So this is the system that we want to solve and get the values of x1, x2, and x3. That's the problem. Okay, so let's take the first equation, a11 x1 plus a12 x2 plus a13 x3 equal to b1, right? So the idea is to keep the diagonal element on the right hand side and push all the non-diagonal elements on the left hand side. So therefore you have a11 x1 is equal to b1 minus all the other non-diagonal elements goes on the right hand side, right? So a13 x3, and then what you do is you just divide both sides by the coefficient of the diagonal element. So a11, if you do this comes. Okay. Similarly, x2 can also be obtained as this one, a22 into b2 minus a22 x a1, sorry, this is a21 x1, right, plus a23. You are leaving the diagonal element on the left hand side and taking all the non-diagonal elements. So this is the one line that you have to remember. Okay, so Jacobi method, I'm leaving all the diagonal elements on the left hand side, pushing all the non-diagonal elements on the right hand side. Okay. And once you understand that, you can immediately write this expressions with this simple idea. Okay, so B3 minus A31 x1 plus A32 x2, right? So these are the terms. Now what you have to do is you have to fix a iterative procedure for it. So what you will do is you are given initial condition x naught, that is a vector x1, x2, x3. Any initial condition can be taken. Okay, Bharti madam has Bharti madam has given some information that the Jacobi method is available in week 5, subjective assignment, and I have answered the queries for it on the forum 2 few minutes back. Okay, so there seems to be a question related to Jacobi method, and it is answered now. And Bharti madam also says the code that was shared from your end, sir, is shared on the query asked by the learner. Okay. I hope, okay, so this is the information that madam is giving. Okay, let's continue this. So once you are given the initial condition, then x1, x2, and x3 at the first iteration can be calculated by plugging in these guys into on the right hand side. So 0, 0, 0, 0, right? So you can just plug in, and now you see these all are just simple expressions, you can calculate that, right? Once you get x1 in that way, again you plug in that on the right hand side. So that you will plug in on the right hand side, and you will put 1 here instead of 0, and what you get as the out of your calculation, you will call it as 2. So again, 1, 1 in the second equation you put, and whatever comes out you will call as x2 of the second iteration. Similarly, 1, x1 you put on the right hand side, whatever comes you will call as x3 2. Okay. Again, once you get the values of x1, x2, and x3 in the second iteration, you will keep that on the right hand side and get x3 and so on. Okay. So in this way, you will generate a sequence of vectors, and this sequence should converge to the solution of your linear system, right? That's the task. Okay, so computationally, of course, you will do some n number of iterations. Okay, so Nasir is asking, can we regard Jacobi and Gauss-Seidel as multi-point iterative methods? I don't understand what is meant by multi-point iterative method. It is an iterative method. Both are iterative methods. Multi-point iterative method. I don't. What is mean by multi-point? If you can explain me, then I can tell you whether it is so or not. Okay, so. Okay, so therefore, here the main point is one thing is you have to learn to calculate the iterations, like x naught will be given to you and a will be given to you, and also the right hand side b is given. Okay, so now you will have to compute x1, x2, and so on. That is one computational question. And the other part of this is we may ask whether this sequence that we are generating, x1, x2, and so on, will it converge to the exact solution? That kind of questions are also answered in our class. Yeah, so what is mean by multi-point? If you can tell, we try to figure out what it is. Okay. Yeah. Okay. So therefore, so this the convergence analysis is also given. Similarly, Gauss-Seidel method is also a slight improvisation of the Jacobi method. So what is the improvisation? It's very simple if you see. I'll probably show through the slides. Yeah. So see, the idea of Gauss-Seidel is once you compute this first equation, okay? So once you compute first one and you got the value of x1, that you can actually plug in this position instead of using the previous iteration. Therefore, in Gauss-Seidel, you will be putting x2 here if you are computing the iteration x1. Then it is x2 here, and then you have 0, 0, and so on. I'm sorry, this is x2 is correct. Okay, x2 is correct. This is x1. Similarly, this is also x1, right? So when you are computing the second coordinate in this second iteration, you already computed the first coordinate, right? So therefore, why you want to use a old value in this position, which is coming from the first iteration, you can just plug in the latest computed one. Similarly, in the third coordinate, you see why I will use x1, 1. I have x1, 2. Therefore, I will try to put x1, 2 here. And similarly, x2, 2 here also is computed. Therefore, I'll put x2, 2. That's at least gives us a feeling that we are getting a better accuracy. It's only a feeling, but mathematically, how will you prove that this will perform better than the Jacobi method. In fact, you can show that. Okay, if both the methods converge, it means the sequences generated by both the methods, if they both converge, then they have the Gauss-Seidel method converges faster than the Jacobi method. This is what you can see from those analysis. Nasir is giving as this one, x is equal to this is 1 point iterative method. Okay. But okay. So this is so Jacobi method and Gauss-Seidel method, they both are 1 point methods. Okay. Similarly, you can get 2 point methods and so on. But in our course, we have only considered 1 point method. Okay. But I think Gauss-Seidel is 2 point method, right? So because just now I just explained that you have to get the second iteration, you are using first iteration as well as the second iteration. Therefore, you can write xk of n is equal to some function of, here that function is these expressions can be just plugged into that function. So it depends on xk n minus 1, that is the previous one. Here you can see to get x2, you are using the values of x1 here, as well as here, right? So here also you are using this, right? As well as you are using x k n, okay, the present iteration, okay? Okay, so but you have multi points within this one. Okay, xk minus 1, these kind of things is this kind of ideas comes in ODEs also. Okay, not in the system of linear equations. In the system of linear equation, you have this kind of problem. Whether can I do this or not? So means your the present iteration values are computed based on only the previous one or previous to previous one or previous and the present one. These kind of questions are more crucial. You can see, of course, this is not just going to be k. So this can, so this is something like, it will certainly depend on all the coordinates of the vector. Therefore, I should actually write vector here, not just components, because you can see here that to get the component 1, these are also x11, x22, and x33 here. Please note down that I wrote only x1, x2, and x3. Okay, 2, 1, 2 here. Okay. So here you can see that there are more than one components which are involved. In fact, it involves the components which are not there in the right hand side. So you don't have x11, right? So therefore, the correct general form of a iterative method for this is given like this, okay, where f is not actually any function, it's also a linear function, okay? So that's how it goes. So the important point here is whether your method is going to depend on only the previous iteration or more than one iterations, including the present iteration. This is the main question. Whereas the question Nasir is asking whether to get xk plus 1, do we have to use only xk or xk minus 1 and so on, is a very relevant question when we are solving the ODE. There we have multi-point methods. Okay, 1 point method is the Euler method. 2 point method is like a trapezoidal method and so on. we have endpoint methods and so on of that. So therefore, this question is more relevant. I hope it comes in the last chapter of our course, comes maybe in the 11th and 12th week of our course. Okay, so that's more, there it is, this question is more relevant. And yeah, we will be doing multi-point methods there, and we will be doing implicit methods where we will be having iterative methods. Okay, so therefore, this Nasir's question will come in week 11 and 12. Okay, so but here the general form will more or less look like. Okay, so therefore, that's the even the right hand side will have a vector. So that could be the correct general form of the iterative methods. It need not be only two, it can be more. Okay, it can be just one or more. Okay, so that's the way these are defined. And then I think we also covered something called uh, the successive over relaxation method. Okay, so this is something like you just put a one relaxation parameter and try to accelerate the speed of convergence, because in all these methods, people generally worry about how fast the iteration converges. Okay, it means whether I will get more accurate solution in 2 iterations or I have to go for 100 iterations. If you have to go for 100 iterations, naturally your computational cost will increase. You see, in all this, if you are just working with 3 cross 3 matrix or 4 cross 4 matrix like that, it doesn't really matter. Okay, even Gaussian elimination method may be good enough for you. But in real-time problems, you will come across linear systems which are very huge, like 1000 cross 1000 matrix or even more. Okay. So in such huge systems, even doing one iteration may take a lot of time. Okay. So therefore, one has to also worry about how quickly I will get in terms of how I want to have less number of iterations, but my solution or approximate solution after that n number of iterations should be very close to the exact solution. So these are the kind of problems, real-time problems that people have. Okay. So therefore, the fast convergence is often interesting for people. So to just illustrate that, we have given the successive over relaxation method where we will introduce a parameter. Okay. And then based on the choice of the parameter, you may get your speed of convergence. So it means you may get more faster convergence. We just illustrated that with the Gauss-Seidel method. The successive over relaxation method basically takes Gauss-Seidel method as the base and then puts a relaxation term into it. And then it tries to accelerate, because Gauss-Seidel, when everything goes well, that is the convergence happens, it gives you more faster convergence, right? So therefore, it's more meaningful to take that and put a successive over relaxation. We have also studied convergence with respect to the spectral radius. So that was also covered in that's a very important concept. And, often in exams, you are tested to see whether you understood that concept. So you have to see the spectral radius of the iterative matrix, not the original matrix A that is given to you. The iterative matrix you have to take and find all the eigenvalues of that matrix and then take the modulus and then find the maximum of that. If that maximum happens to be less than 1, then for the iterative matrix, okay, then this the sequence generated by that method from where this iterative matrix is coming, Now that method will surely converge, and it is a necessary and sufficient condition also. So these are the important points that we covered in the linear system part, and then we went into the eigenvalue problems. Okay, I think that would have happened very recently. Therefore, I don't know whether you have covered them or not. If you have not covered the eigenvalue problems part, then it is not very meaningful to talk now or recall now. Anyway, time is also up. Therefore, we will stop our discussion here. I expect more people to join for the live session to make our session more lively. And also ask many questions. Thanks to Nazir, and also Nazir asked and Chetan asked. So two students asked question today. Thanks to them, and I hope you will continue to come for the live session and interact with me. And also more students, I invite you to come for the live session, because this is an excellent opportunity for us to interact with each other and get to know our learning, and also interact and learn more also. Okay. So with this, I thank you very much for your time in this live session. I look forward to meet you also more people in the next live session. Thank you very much.